Hello everybody. This video is going to be talking about the lesson for 10-6, focusing on geometric sequences. So a little bit of a review of Algebra 1, but obviously we're going to learn a lot more new stuff as well. So you should have heard about geometric sequences in Algebra 1 when we talked about arithmetic sequences. So a geometric sequence is a sequence, which remember a sequence is a list of numbers separated with commas, and for geometric it is multiplying by the same value each time. That also could be referred to as changing by a common ratio. So it's multiplying. You could also understand it as dividing, but we're going to focus on what number it would have to be multiplying by as the primary change here. Right, so geometric sequences, so looking at the first one here, we have 6, 24, 96, 384, and then so on, it continues, right? So just identifying first of all that it is multiplying by the same thing every time. To get from 6 to 24, it would be multiplying by 4, and then if I test that out for the rest of them, it should be multiplying by 4 for the rest of the numbers so far in the sequence, right? And we could continue the pattern down for as long as we want. So there are ways we can write equations to help us find certain numbers in this sequence, and we can use it eventually. We'll find the sum of these big long, when we write them as series with the plus signs. So we're going to come up with these equations, that nth form equation, to help us if it is geometric and multiplying. So going back to how we first learned this is most likely in the first term form. And this is very similar to exponential. Exponential growth is multiplication, and the exponential equation, the parent function is a times b to the x. So it's going to be similar to that format. Instead of using the x's and y's again, remember that means that there's points and values in between all of these numbers. So there, after 6, maybe there's a 7 or a 6.5 or something, but in this sequence there is not. So we're not going to use the variables x and y. We end up using that t of n and n. Right? So that just shows that there's the numbers are separated, they're not connected and continuous there. So t of n, then normally we do the 0 term, which is the number before the first term, and then in parentheses, I'm going to use the word multiplier, and then we had an n up there. All right, so this is how maybe you were familiar with it before, possibly. So t of n, 0 term, so that means the term before, this is the first term. The first one printed is always going to be assumed that's the first term, so we need to go backwards before this. Now if our pattern moving to the right is multiplying by 4, I need to go backwards. I'd have to divide by 4. Right, so I really have 6 divided by 4, which is either you can leave it as a fraction. I'd probably prefer that we reduce the fraction to be 3/2, or you could write it as 1.5, 1.5. So either the 3.5 or the 1.5, we'll write that for our 0 term. And then we obviously figured out it's multiplying by 4, so that'll go in the parentheses, and then we have an n, right? So this is called the the 0 term form because you're using that 0th term. However, like we did in arithmetic sequences, we're going to use this different format. We're going to use the first term form more often as we move forward in our math topics. So it's basically very similar. T of n, instead of the 0 term, we're going to have the first term, and then I'll have the multiplier. And then just like with the arithmetic one, we had, instead of just the variable n, we're going to have n minus 1, and all of that's in the exponent this time. Right? The n and the minus 1 is in the exponent. So the first term form should be easier for you guys to find because you don't have to go backwards before this first number that's printed. So first number is 6, right? So that's that. And the multiplier is 4 still, and we're just going to have n minus 1. So it should be a little bit less work for you to find the first term form. I think you're figuring that out from the arithmetic ones that we've been doing. So it's just the first one printed there, and then our multiplier raised to the n minus 1. There is a slightly different format with notation, like we had with The arithmetic ones, we could have a sub n instead of this t parentheses here. And maybe we'll say a sub 1, meaning the first term, and then parentheses r raised to the n minus 1. So that r, the reason that it's an r here, this represents like the change each time, and that's because we kind of refer to it as a common ratio that it's changing by, whereas in arithmetic, this might have been the variable d to represent the common difference. So it really is just what's it changing by is really what's going in this parenthesis here. Okay, so we're going to stick with this first term form more as we move forward. It's going to be important, and then I don't really care which of these notations you use more often. You can check with your teacher and make sure that maybe they prefer one format over the other. Okay. Last question, or last part of this question, is just finding the sixth term. So just practicing plugging in 6 in the n spot. We should be able to use either equation here and get the same thing. So just to kind of prove that, I'm going to use the 0 term form first, and then I'll do it in the first term form. And really the thing with these equations is just making sure you plug it in the calculator correctly. So I have 1.5 times 4 raised to the 6th. If I use this format, that gives me 6144. That's the sixth term, would be 6,144. And I just want to make sure, again, that you're typing this in okay. Let me try to move that a little bit. So if I type in this one, I just have an 84 here, but 6 times 4, and I'm raising it to the 6 minus 1 power, which you could just change that to 5, but make sure when you're typing this in, if you do leave it as something minus 1, that both of those are, in fact, small numbers in the exponent there. So again, we get the same thing. So, proves that both equations are perfectly functioning, but we're going to prefer using the first term form as we move forward. Okay, so if I wanted to find the 12th term or the 100th term, same as we did with arithmetic, we're just going to plug in that term number we want in the n position. N stands for the number of terms, or the term number. All right, number 2 is basically the same thing, but just a little bit different. So we're going to have some practice questions at the end, so if you feel like just trying this one out, go for it. But I just wanted to point out that it is changing a little bit differently, but it's still a geometric sequence. So we want to write the equation in first term form and find a sub 12, which that's just a different notation, meaning find the 12th term. So we have 500, and then it goes down to 125, then it goes down more to 31.25, and continuing on like that. So you might think, okay, I think it's dividing by something, and it's dividing by 4. However, our equation, I use the word multiplier kind of on purpose here because we want to make sure we're multiplying by something. This equation is set up based on it being multiplication. It's multiplied by a common ratio every time. So you can't just write like a division sign and a 4 in the equation here. So we need to figure out what could I multiply by that means the same as dividing by 4. Well, you can multiply by either a 4th or write it as 0.25. Either one of those will still get you to the same thing, and it'll continue as we move down in the sequence. Okay? So just make sure if your sequence is changing by you perceive it to be division, figure out how can you get from one number to the next by multiplying, because this equation, we have to use the multiplication aspect of it. So writing our equation in first term form. First term, 500, that's pretty easy. And then we figured out it's multiplying by either you could write the fraction 1/4 or 0.25. And then we're going to have n minus 1. Again, both of those are in the exponent. And finding the 12th term, maybe I guess I should have written this as a sub n, since this notation has a sub 12. But again, it's just more of understanding what this notation means. So plugging in 12. Again, this part should be pretty easy as long as you're just typing it in correctly. 500, and I have a parenthesis 0.25 raised to the 12 minus 1. Oh boy, I get some crazy thing here. So I get like 1.192-ish, and then it says E with a -4 on my calculator. I just cut them off at some point here. Your calculator might show something different possibly, but just so you know what this means, this E here means scientific notation. It means 1.192 approximately times 10 to the -4th power. So that means this is a very small decimal. So instead of leaving it with this scientific notation or this E, we can, maybe you've done this before, I hope, in earlier years, we can change this so it's written in actually as a decimal. So this is a -4. That means we're going to change this decimal point to the left 4 times. So 1, 2, 3, 4. That's where it's going to become. And these like little blank spots, I like to leave those little bubbles and then fill them in with zeros. So really our 12th term is 0.0001192, and then if you kept more decimals places, then you can have those there. Okay. So again, that makes sense because our numbers are getting smaller as we're going because we're multiplying by a fraction. So just think, to yourself, does it actually make sense what I'm getting? All right, new problem here, example number 3. In the sequence below, find the number of terms if the last term is this 229,376. And I didn't put in the commas just kind of for this entire lesson, just because I didn't want to confuse you guys to think, is that the next term or whatever. So technically you could put a comma in there, but just to hopefully avoid some confusion. So we're going to start with the first term form equation. That's kind of our go-to right now. So we're going to set that up. I have my first number is a 7. And again, if it's a geometric sequence, it should be multiplying by the same thing every time. Very obviously times 2 times 2, so I think that's our multiplier, raised to the n-1. So we have the last number here, but we want to know what order that is in this list of numbers, right? Is it the 10th number? Is it the 15th number? So what we can do, like we did with arithmetic sequences, is I'm going to replace this entire value right here on this entire side, right? And then if I solve for n, that will tell me the term number this is, and then therefore, since it's the last number, that's how many terms there are in this sequence. So I have 2, 2, 9, 3, 7, 6 equals this side. All right, now solving this is a little bit different because we have a variable in the exponent. This is going to bring back some of the skills we've learned earlier in the year, and it's going to kind of tie things together. So first we want to get rid of, we're going to try to isolate this variable, so we're going to get rid of the 7 by dividing by 7 on both sides. So that is 3, 2, 7, 6, 8. So now I'm just left with 2 raised to the n-1 power. So okay, problem, we have a variable up in the exponent, something we did, I don't remember if it was the end of the first semester or just when we got back, but we added logs in to the problem. So if I take the log of both sides, right, logs are the inverse of exponential things, so that's how we're able to do that. And once we put log in, now that brings this either down, and you can put it in the front of here, or I just wrote n-1 behind it, right? This is kind of connected still. So putting log, as long as we add it in to both sides, we take the log of both sides, that brings our exponent out of the exponent. So we're still trying to solve for n, so I need to get rid of this log of 2 before I can get rid of this -1. This is still a quantity kind of stuck together here. So I'm going to divide by log of 2. Make sure as you're typing this into the calculator, depending on what calculator you're using, that you close this parenthesis. So let's see. Try to show that on here. So I have log 3, 2, 7, 6, 8, and I have to close this parenthesis up myself. If I don't, it's going to just divide by log, oops, wrong button there. It's going to divide by log of 2, like within this top logarithm. So we don't want that. So we want to close that parenthesis up, then divide by log of 2, and we get 15. So this whole side turns into a plain 15. and then equals n minus 1. So then, to simply solve for n, we'd add 1. So we get that n is 16. That means this is the 16th number in the list. That means since it's the last number, that there is a total of 16 terms. Okay? So make sure you're using logs if we need to get that exponent or the variable out of the exponent. All right, one more example, then there's going to be some practice questions for you to try based on all of these. One last one that's different. Example number 4. In a geometric sequence, the 5th term is 64, the 12th term is 8,192. Write an equation for the nth term, which basically is that first term formula. So we might be referencing that a couple of different ways. Write an equation for the nth term, that's the t of n with the multiplier and the n minus 1 stuff. So, to find that nth term equation, we need the first term, we need the multiplier, and then we put n minus 1 on the top, right? So we don't have any of that information so far. We can't very easily figure out what it's multiplying by to get from 64 to this unless you just try a bunch of different things for a bunch of different times. So you could do that, but that might take a little while. So remember, geometric sequences, they're multiplying. So it's very similar to exponential, like we said in the beginning. So I'm just going to modify this equation just a tad, just to bring it back to a little bit more familiar variables. So if I just kind of adjust it a little bit like this, I can write these pieces of information as a set of points. You could also keep it as n and t of n, because the 5th term, n stands for the term number, and this is like the value of the term. So whatever makes more sense to you, but basically we could write these as a set of ordered pairs. So I have 5 and 64, and then 12 in this 8,000 number. All right, so I have two sets of points. So I'm going to plug those into this either format really, based on, it just depends on what variables you're kind of going off of. So, and we can solve this like we did earlier in the year. So I'm going to say 64 equals a times b to the 5 minus 1. So just plugging those things into this format here. Right? We need to figure out what the first term is and what the multiplier is. And instead of writing those words, I'm just using those variables. We could go back to a sub 1 and an r, but the point is basically you're going to solve for two unknown values here. So I'm going to do that again with this ordered pair. 8192 equals a times b to the 12 minus 1 power. I'm just going to simplify the exponents. It's pretty simple to just subtract 1. But I'd probably do that, write it out first, and then subtract 1, or else you might make some mistakes. And then what we did earlier in the year is we stuck the bigger exponent. I focus on just these two things now. I put the equation with the bigger exponent on the top, because what we're going to end up doing here is I want to eliminate one of these variables. And if I stack them up like this, if I were to divide this equation by this equation, a divided by a cancels out, right? So I just have to divide everything here. B to the 11th over b to the 5th, I'm really subtracting my exponents here. So if I always start with the bigger number for the exponent on the top, when we subtract those, it'll always work out to be a positive exponent here. So I divided the a's, I divided the b's, I'm going to divide this side also. That's going to give us 128, I believe. Oops, you know what? I messed up here. So hopefully you're paying attention. I didn't subtract 5 minus 1. That's not 5 anymore, right? That's only 4. Hopefully you caught that. And then when we do that, now it's b to the 7th. All right, so to get the b by itself, which is basically the multiplying number, or that common ratio, we're going to take the 7th root of 128, and that should give us b equals 2, which means it's multiplying by 2 each time. So we've got that part, right? We've got this part of our formula. The whole point of this question is to write this nth term equation, is to fill in this stuff. So now we know this part's a 2. So I'm going to plug this back in to either of our two original equations to try to find a, or that first term. Or you could just go backwards and divide by 2. Start from 64, divide by 2 a couple times till you find the first term. Right? But I'm going to plug this back in, plug it into this one, just because it seems like smaller numbers. And then 5 minus 1, that's a 4, and I won't mess that up again. And so then we're just going to solve for a. Remember, in our order of operations, we would do the exponent next. So I have a times 16, and if I divide both sides by 16, we will get 4 is our first term, right? So they're very similar spots here. So we're just going to plug them in. So our equation in the nth term, right, just putting our pieces in where they go. We need the first term, which is what this a stands for, so 4. And then times the multiplier, so we multiplied by 2 each time, and raised to the n minus 1. Okay. So this setup here, hopefully that seems a little bit familiar, and then just starting out by putting these into ordered pairs to plug them into this equation. So the rest of the questions on here are practice, so if you want to go ahead and try them yourself and then just check back on the answers, try doing that before just following along blindly, okay? So practice questions, give them a try. And we'll go ahead and go through. Okay, so practice number 1, write the equation in first term form and then find the given term value. So this is like example number 1 and 2. Okay. First term form, I'm thinking that this is multiplying by 5. Right, so my first term's 2, multiplying by 5, and minus 1. So that's a geometric sequence, so follows that same pattern. Then we're going to find the 10th term. Right? So maybe I'll change it to a sub 10 over here instead of t parenthesis 10. 2 times 5 to the 10 minus 1. So just plugging that into your calculator now. Again, careful that you are, first of all, making these both the exponent, and you're including that minus 1 in your equation up there. So I get 3 million something. 3,906,250 is our 10th term. Okay. Second one, we have a starting value of 9, or the first term is 9. And it looks like it's multiplying by 3. And minus 1. And we're going to find the 8th term. So again, this is just plugging it into the calculator. 9 times 3 raised to the minus 1 is 19,683. Check you're getting those okay. If you're not getting those and you have the right equation, it's probably something with how you're typing it in. All right, practice number 2 is just like example 3. In the sequence below, find the number of terms, which means n, if the last term is that 118,098 number. So we're starting with that first term form equation. Starts with a 2. It's multiplying, looks like, by 3. And I'm going to replace, I don't know how many terms there are, that would be this n, but the t parenthesis n represents the value, or the, I guess, yeah, the value is the best word I can think of, the value of the number in the sequence. So 118098 equals this side. Right? So we have to do PEMDAS in reverse here, so we can't get rid of this exponent first. We're going to have to do, right, if you do PEMDAS. There's nothing that's added or subtracted just alone, right? This is in the exponent that it's added or subtracted. The next thing we'll do is deal with anything that's being multiplied or divided. So we're going to get rid of this 2 by dividing by 2. So that's going to give us 59,049. And we have 3 raised to the n minus 1. So again, we have to use logs to get this variable out of the exponent. So I'm going to take the log of both sides, and then once I do that, that brings my n minus 1 down either in the front or behind it. I'm going to put it behind it because I don't really have any room in the front. Right, as long as it's being multiplied, it doesn't matter if it's in the front or the back. So we're trying to solve for n here, so this is still like a chunk together, so we need to get rid of this log of 3. So again, as you're typing this in, oh boy, poor next little problem. As you're typing this in, make sure you close the parentheses. I get, when I divide log of the 59,000 by log of 3, I get 10. And then this side is just n minus 1 still. Final step is you add 1. So we get this number here is the 11th term number. And since it says that's the last one, that means there is 11 terms in the sequence. Okay. Last practice question here is like the example number 4. I'm going to try to erase this. Sorry. Hopefully you have enough room if you're writing these down as we go. In a geometric sequence, the 4th term is this, 9th term is this. Write an equation for the nth term. So I'm going to go ahead right away and write these as little ordered pairs. And I'm going to plug them into the equation, very similar to an exponential equation, but remember it's going to be raised to that like n minus 1 power. So maybe I'll say this is n and this is t of n. What we're trying to make it look like, right over here, we want the first term and then the multiplier to the n minus 1. So we're plugging these things in to this format. So I'm going to have this 375 be over on the left of one equation. And instead of writing the words first and multiplier, you could write a and b. You can write a sub 1 and r. Maybe I'll try to do that so it's a little bit more notation, sound notation, and then raised to the 4 minus 1 power. All right. Same thing over here. 1171,875, that's a big number. A sub 1 times the multiplier raised to the n minus 1, and n in this case is 9. So I'm going to subtract the actual exponents up here, and then I'll stack my equations. I know this number is really big and it's annoying to write down, so sorry about that. Okay, so I'm going to stack these equations on top of each other. I want the one with the bigger exponent on the top, just because when I subtract the exponents, it will give us a positive number. So I'm just going to kind of rewrite this one underneath here, taking the easy way out, and I'm just going to focus on like these things right now. So if I want the a's to cancel out, because they're both a to the first, I'm going to divide that. I'm going to divide these r's, or if you called them b's, it's whatever. To me, I'm not really that particular about it. Mr. Boyd might be, I'm not sure. But as long as you're understanding what's happening with the exponents, I think that's probably more important. And then this side we're going to divide as well. So this big long number divided by 375. It looks like it's going to be a 3125, hopefully. And then if I want to solve for this variable, I need to undo the 5th power by taking the 5th root of both sides. So we get our multiplying number is 5. Okay. So that would end up going right here in our equation. So right now we know it's going to be a 5 in there for our final answer. Oh, sorry. And then we're going to plug this r value, or this multiplier value, back into one of these equations. I'll probably do this one again just because it's smaller numbers versus writing this a bunch of times, because that's annoying. So 375 equals a sub 1 times 5 to the 3rd power. So again, we have exponents before the multiplication, so we need to do 5 to the 3rd power first. That equals 125. Now those two things are multiplied together if I'm trying to solve For that first term, I'm going to divide by 125, and we get 3 is the first term. So I can just replace that up here, because the goal was to write our equation in first term form. And we could check this very easily by plugging in a 4 in the n spot, and do we get out 375, right? I'll just test that just for fun. So we have 3 times 5 to the 4 minus 1 power, 3 times 5 to the 3rd power. Again, following those order of operations, we'd have to do 5 to the 3rd. So that's 3 times 125, which, yep, that gives us the 4th term is 375. So just a way to check your equation is working. You could also very easily check this on your calculator. You just have to change your variables a little bit. How can I put this right here? So on my calculator, I don't know which calculator you're using at home, but you can type this in like it's an exponential equation. So I'm going to go into where it says y equals, and I'm going to do 3 parentheses 5 raised, instead of n, I honestly haven't tried n, but I'm going to just stick with x because I'm not sure what else it would do if I put n up there. So if I just change those variables a little bit and I go to the table, it should tell me here the 4th number is 375. I could go up a little bit more and see the first number is 3, right? Here's my pattern, it's multiplying by 5. Let's see, the other one we had was the 9th number, so it's shortened in the table, but it's this big long thing. So that's a quick way to check your equations are right if you have access to a graphing calculator like this, where you can enter the equation in that y equals and create a table from it. So reach out to your teacher if you're still having trouble with anything. Great job, guys. Keep it up.